Zoom बंद रहेगा अभी तक last time we looked at possible examples of convex sets. Another example before we go forward. Non-trivial example. Proceed. Oh, so what is the definition? We said a set X. So interchangeable using X and S. So if you find it confusing, bear with me. So we said X is convex if X1, X2 belonging to X is such that lambda X1 plus 1 minus lambda X2. Then try to avoid writing through because this sentence to be always, if I write something like this, it's a convex combination. So unless it's specifically written something else, always assume that that is true. Okay. So now what happens if there are k points? So you have x1 through xk belonging to chi. Can you extend this definition to k points? Should belong to X. So this is an implication, right? That's not a definition. So lambda I, xi should also belong to X for I is 1 through k, or summation lambda I equal to 1 and lambda I is greater than 0. So is this an implication of this or is it a definition? Yeah, why is that true? We are expecting this to be true. If our definition is G global, we would expect this should also be true. Right? But the definition really involves pair. But now I'm taking a collection of any k points. And I'm calling a set convex. If X is convex, this better be true. So I think it's a way to prove it or give me a simple argument. Can use induction to. That's brutal. Is there anything nicer? Or we might simply say the pair is by definition, so this is trivial. Is it trivial? It trivial be true. Or we need to do any work to get this. And if it is not trivial, what other difficulty? What will potentially be required to be shown? Induction is definitely an option. But that's kind of a brutal option. Is it something nicer or cuter, which one can do? So the believe is true. Oh, that's the first thing to understand. The definition doesn't tell you that this is not necessarily true. We want to show that that implication also tells us that this is also true. So what is going on? So for any 2 points, x1 and x2, we have that the full line is contained in X. That's all we know. Now given this x3, let's say just for 2 points. What are we asking? To take a, so what would it lie? Where would this point lie somewhere? Let's say here. Okay. Now we are asking this better be also contained within X. From this picture, can you at least convince yourself that this better be true? This is convex. So we know all these lines are contained in X. That much we know. And X is convex. That much we know. So why is like this point is also contained in X?
Because there is a point on the range x1, x2, which passes through x3, that point, and the point on x.
Sorry, I didn't catch that. The point on X1, X2,
Yes.
which
That is a straight line passing through this point, the point in the middle, and x3.
right? What are you going to claim this?
Because the convex side, so the line connecting that point and x we should also like the side.
Very good. So, but why should it this point on that line? So we choose a point. So, but we need something from Euclidean geometry to claim something.
Continuity.
Continuity. Not continuity, something else. What is in fact the claim? So we take a non-trivial combination. Let's call this point as a vector lambda1, lambda2, lambda3. That's fine. Now what are you trying to say? Make your statement concrete. You're trying to say there exists a point A. There exists a point. Let this. So that what property you demand?
It's that the light passes through a real light. That passes between x3 and lambda1, lambda2, lambda3.
Such that the line or the extended line, let's call it, line connecting, let's call this X, X and X3 passes through. Okay. Now what shall I do? That might be also given, let's say. Now what?
So we have that A is a linear combination of x.
What we know is that for a pair, now forget about this point, by definition belongs to this line. And I know that A belongs to X, X3 belongs to X. So this point better belong to X. This is the order in which you constructed. I don't know anything about this point. What I want to show that this point belongs to X, but I know that this point belongs to, by definition of X1, X2 over pair, X3 by definition belongs to X. So this line also belongs to X. So any point lying on this also belongs to X. So better be that this point X also belongs to. Okay, so how do I extend for more than 3 points? We'll keep doing this and then ask, like, it's not a really game way. So I'm not trying to show that convexity implies this is true for every such combination.
For iron, in the general case, you can just go in that order. But what you can do that for not taking the plane or for a single line, go 2 lines, take a for the R3, you can take a plane and another line passes through that plane, extend it.
So what's the punchline of this argument? With 3 points, what did we accomplish really?
Get a triangular region.
Sorry, I didn't catch.
Get a triangular region.
No, that is not the punchline. Immediately, yeah.
So first we took lambda one, say lambda one and lambda two, they add up to 1. So first we took the convex linear combination of x1 and x2. And so then we took another convex linear combination of that point that lies in x1 and x2 with x3. And then we kept on repeatedly doing that.
So all we have to know is that for pair we already know what convexity means. So from 3 points, you're reducing all multiple points to a pair. That's all we're essentially doing. So that's similar to the idea of imagine. That if you know something from, let's say, k minus 1, how do you go from k minus 1 to k? So now can you give me a pictorial or a non-inductive argument to make this work for any k? Very simple argument compared to induction. Okay.
By the objection.
Okay. So now that's choice. So it's not.
So suppose it is not true,
Yeah.
then there will be a set of lambda i's
Yes.
such that the.
But set of xi also. So you have to work with both.
Yeah,
So you can't simply say that there exists a set of lambda I for any combination of x1 through xk. It might be some x1 xk's are the ones which don't work.
you can do both.
Both.
Like, suppose we are saying that, first what we are trying to do that for any x1, xk, we are claiming that there will be, take any lambda I with the property, it will be in x.
Yeah.
If not true, then for a particular choice of x1, x2, xk, there will be a set of lambda i's such that
It don't work. And that's where the problem will start.
yes.
In your induction, in your contradiction argument, that's where the problem will start. That's what will make it slightly harder to prove that. So it could be that the lambdas xi don't work. So when we only show that it works for every possible collection of x's and lambdas. When you go in the contradiction way, it could be that the lambdas for which it doesn't work depends on xi in some non-trivial way. I'm not saying it's not possible. That's where the difficulty lies.
It could be a function of the lambda is can be the function of x.
Yeah, but they may not be independent. That's the whole point. Now, independence should be taken in a probabilistic way.
We don't need a function, right? We just need one pair of x and lambda.
No, that is the forward direction. You want to reduce it down to a pair essentially. What I'm trying to do is to prove a contradiction. Suppose there is something like this, it doesn't belong to x. Now it contradicts me. I'm not saying it's not possible. The trouble with that is you have to work with both lambda and xi simultaneously. You can't find one and then try to work with the other.
Yes, in both of them.
Okay. Let's hear. Yeah.
So I'm saying that first increase one, do with the other.
Yeah, but that's not sufficient. That's not the way you simultaneously do it. That's all I'm trying to say. That will not be sufficient to finish the plan. You have to work with this.
If you are saying that, so if we have, if the for any pair and for obvious choice of lambdas,
Yeah.
so if that doesn't work, then we'll have set of xi, x.
Okay, let's try to do that. Let's see where we end up. So contradiction. Suppose there exists a collection x1 through xk and lambda 1 through lambda k such that lambda I is 1 and lambda is greater than 0 such that summation lambda I xi do not belong to x. Now, remember this. Now, what will we try to do? Now to somehow prove the contradiction to the fact that X is convex. And my definition of convex is take any pair.
Yes.
Yeah.
So call it Y. What we are trying to,
Call what?
just to not to make that summation.
The summation.
Yeah.
Okay, let's call delta. That. And the fact that it doesn't belong to X, what information is being revealed?
So if you, that is the point. And if you try to join a line from each other point.
Okay, so this is my X, let's say.
This.
I should have drawn it convex. Okay, and now somehow delta belongs here.
Yes.
That's what it means. While my Xi were inside. Okay, now what?
So distance between delta and X is
Non-zero.
non-zero.
Right. But why is it disproving the fact that X was convex?
So if you take any point inside
Mhm.
and take a linear combination of the delta and that point,
These points or some other special points?
miss any point. No, this point.
Okay.
Then our part of the line will be lie completely outside that convex set.
That's okay because delta is now a part of X. So that's not necessary that the full line should belong to X. It doesn't help.
Somehow we have to show that in one of the exercises will not be.
Something has to be shown to prove that this is gonna work because delta, by your definition, it actually lie outside. And there's no guarantee that the full line belongs to X. So delta necessarily has to belong to X. So what if 10 was just to open this argument? Work?
My definition it should belong.
No, delta is just sitting outside. This n means this. Okay, so by definition, delta is inside. So, okay, so let's take it 3 or something. 6. Now, the idea that delta is, if it is outside, don't tell me that it can't be outside, because that's the point in the proof. The fact that you're taking delta outside, that is contradictory. Somehow the convexity of X has to be contradictory. So you can possibly start doing the convex hull of X1, X2, X1, and say that delta better be belonging to the convex hull. And convex hull at these 3 points better be sitting inside X. So this is not, that's one way of progressing.
The cyclic definition of convex hull coming back to this definition.
No. Convex hull definition didn't require this. That is going to be pairwise.
Yeah, we didn't define convex hull yet.
Okay, so maybe I forgot. The operation came out of convexification from the convex hull. So we find the operation of convexification. That essentially on the end level is called the convex hull.
So yeah, we can use that. We can use not convex element basically. So that convex set X contain that X1, X2, X3.
Yeah.
And we know that there is a set convexification of X1, X2, X3. That is the smallest convex set that contain these 3 points.
But that's precisely where the convex hull is.
So I am not. So since delta is a point in the convexification, that means it should be.
That's what I said. I was repeating.
Why is delta inside?
That is the definition. That you can prove that it better belong to the convex hull of
And it is the smallest convex set that contains.
smallest here. The smallest property is not being needed. Now, why am I needing the fact that it's smallest?
Because X, the capital X is also a convex set that contains these 3 points.
Yes. Oh, so you're saying the convex hull will be contained inside capitals? Yes. That is true.
So that delta cannot be outside, that is the concept.
Yeah. So delta will be sitting inside. So that's one way of doing this. So now let's do the brutal way. The brutal way is just do induction. I don't like it because it doesn't work for me. But let's do it. Everybody got what is needed here. So you can take any key points and let delta sit outside. Now, given the fact that these key points are in X, look at the convex hull of that. Now, this delta belongs to the convex hull is straightforward. And the convex hull is also the smallest set, convex set containing all these points. And then that will be contained inside the capital X. So then delta is a member of the convex hull. Convex hull is a member of X. So that will be the delta belongs to X. That's the simplest geometric way of looking at it. Okay, so now.
Why did it reveal the data mass line and convex simplification?
Okay.
Just define data. Convex simplification says that any two points that you connect.
Yeah. What the one?
Yeah, any two points that you connect, let's say X1 and X2.
Yes.
Then the line connecting them must lie outside the.
No. So what was convexification idea? Because not those points, they were resulting also.
Yeah, so whatever resulting,
So you can this, so let's just try to do convexification discrete. Just X1 and X2. This is the line you use. I will get another line with this operation. Another line doing this.
right,
Now start with alternate lines. You will essentially end up filling all this area.
right,
Okay. Now what is the problem? The problem is that doesn't belong here.
yeah.
Okay.
So
So
you do that. Because
mhm.
it doesn't follow review.
It's not clear.
Okay, yeah. Because it's less than the summation is less than.
Is everybody okay with it?
That is the induction that we have to open the first case.
So that's the completely different. Now, what I'm asking is, does this element belong to the convex hull of X1, X2 to Xn?
Basically, the point is that,
That's another way of looking at it. Yeah.
yeah, so, all the lines can be, on the line, any point can be joined by lambda, lambda one, lambda two of.
Yeah, you can use that also, but then just to show that. Okay, so how about doing this in a effective way? We number two value. So we just prefer.
Or and less than.
Oh, let's try start with the basic case. Yeah, so K equal to P by definition, so we can start. So let's suppose it is true for any n minus one. N minus one to n.
Okay, that's one. Okay, 10 points.
So what do I have it is? By this, I have summation lambda I equal to 1 for equal to n minus 1, such that lambda I xi belongs to x. This is what I'm saying. This is what I'm doing. Okay. So how do I add one more point, make sure that the summation of lambda is 1?
So the lambda and
So multiply that with lambda and add it with xn into times 1 minus lambda.
Sorry, I'm not following. So what should I multiply with what?
So that thing right inside
This one or this one?
this
Let's call it delta n minus 1.
delta n minus 1 right inside it.
Yes.
So lambda times delta n minus 1.
Which lambda?
Any
One of these? Something not equal to this? Okay. So lambda times this.
plus 1 minus lambda times xn.
Yep.
So that is why right inside it.
That belongs to,
Right inside it, right.
yeah, for Yes, this is true. Okay. We're not done yet.
So let's say we wanted lambda one, like let's say lambda one.
You see why we are not done, right? Because if I open it up, we still need to prove to me that the product of lambda times lambda I sums up to 1.
You want to prove that the coefficient of that, whatever you are getting mean wise, that
Sums to 1.
and you have already that summation lambda is, yeah, sum up to 1.
That I have, yes.
Yes, so lambda is,
So all our quantity is not done yet.
yeah, so
I'm
lambda,
not saying this is a wrong approach.
so lambda is a common factor of all of them, lambda is.
So I want me to multiply, I'll multiply. Right? You did that, putting it there. Oh, now what do I get?
Take, just calculate the coefficient, number of coefficients. We're looking at the coefficient, so the first n minus 1 coefficient has a common factor lambda.
So what do you want me to do? Lambda times lambda I.
Plus 1 minus lambda equals to 1.
Yeah. So now lambda comes out. This summation is 1 plus 1 minus lambda is equal to. Done?
And I have to prove that all of them, like 0 and 1, and that is.
That is okay. Because by design, this is true, that is also true. So that's not important. That's not required to be.
You're still not shown that also all lambda one, lambda. You show that there exists a certain, like certain tuple lambda for which this works. We have to show for all such lambda. So then we can take, like, let's say,
No, why are we not done?
we have lambda here.
This lambda is arbitrary.
Right.
This lambda is also arbitrary.
Yeah.
But the things you have produced, they're very specific. You're not produced for all possible lambda. You're saying this type works. Doesn't mean that every type works. And the deficiency in this argument. Because not every number is of this type, right? Lambda times lambda I. So there should be some more direct way of doing this.
Let's take that summation mu I I equals to 1.
Just for a second. How do you make it work?
Let's say we had some lambda one prime, lambda two prime, lambda prime.
Yes.
So we already have, so take lambda and prime to be 1 minus lambda. And the remaining we can divide it down.
Something like some normalization, you must have seen this in the videos.
Scaling of first.
Yeah, just need to scale it appropriately. That's all you need to do. So leave that as an exercise. Now we see what the gap is here. Not true for all. What we are not shown is that for all possible lambdas. For certain special lambdas you are shown. So what you need to do is you take this combination and renormalize that appropriate quantity so that the overall sum becomes 1. That's all you need. And then we can apply to the induction problem. But from n I can get n minus 1, and that n minus 1 it works, and then it will work. So please do the exercise. It's not difficult. Don't you stop me every time. Okay? Nothing to do it here. So please better lessons today. You already know better with me. That is a cone. So let's say a set. If it belongs to C, theta X also belongs to C for any theta. Very simple set. That's how you define anything, should give an example and count example. So that's the most obvious example of it. No? So I don't know.
Take the models and rotate it.
Simplest type. What about zero?
Yeah, okay.
Singleton doesn't work anymore. It has to be zero. See, for convex set, singleton is okay. For cone, singleton is not okay. Anything other than zero. So, example 1. Okay, next non-trivial. So it should be just something.
A line,
And
plus half line,
What is this half line?
like x greater equal to 0.
Why is it necessary that x is greater than 0?
Greater equal to 0.
Why? Why is it necessary that x is greater than 0?
Then not as unless
Okay. But I would simply say the x-axis, all of x-axis is fine. So y equal to 0. Okay, let's just write it this way. Similarly, you can switch it around. Oh, next one. That is rotation on this line.
and ask.
Yes.
So take two lines
Yeah.
and take the convex integration of them.
See, now line is what? Extended to infinity, what?
You can take two line y equals to m1x, y equals to m2x, such that y greater than equal to 0. Take the convex integration.
About this.
Yes, yes.
Yeah. What stops you from doing this one? When stops you, right? You can. Essentially, this is also fine. That needs to be greater than 0. X doesn't need to be greater than 0. Okay.
But I said y greater.
Why? That's what I'm asking.
I is given.
Yeah. So, see, everything minimal should be there. The requirement should be there.
Any union of two points.
2 points to the point.
Definitely, that's nothing about complexity.
Yeah, we're not saying anything about complexity. Yeah. So suppose we have a column like this. It's going to infinity. Yeah. Now, median means what? Take any point which belongs to either of the two. You scale it up, it still exists. So union is fine. I'm not saying anything about convex. If you take a point here or here, it will extend and still be part of the union. So union is fine. So if you have 2 cones, you can just simply take the union of the 2 cones. Okay, now what about convexity of a cone? By definition, is it convex? So that's an example.
This one,
Okay, something simpler.
That two lines.
two lines.
No, that previous example only.
Which previous example? This one is definitely.
Remove that. That also.
This one?
You remove, yeah. If you remove that also, that is not convex.
Yeah, because this line is not. Yes. The simplest one, I think, is the following. You take x axis and y axis.
There's no point. Oh, that's correct.
Exactly. So just this way and this way. That is also. It's really enough so on. Anything other than more interesting, which is not the union of cones, which doesn't end up being convex. Think about it. So now convex cone, a cone that is convex is called convex.
Yeah, so
Sorry.
I just give an example. Yeah, can I have given an example. So where it will not be convex.
I never said that every cone is convex.
Yeah.
Our convex cone is convex.
It's another example of which is not convex.
Yes.
So take any two cone and take the symmetric difference of.
That's difficult. That's actually not true. If suppose there is some intersection like this, what will you end up getting? This part and bottom part? It's the same thing. Usually.
It's not very good.
But it ends up looking like you know some other two ones, some other two ones. No. What are you trying to do? You take one call. Right? And let's say I have the color file not using. So another call. What are the which part? This part clearly, this is clearly one. So here could be this, union this. What are we going to look at?
I'm saying that it is not always true. It will be a union of two cones. It can be a single point. Means it can be empty also.
In this example, what is your symmetric significance?
This.
This is it.
Yes.
So it looks
No, but the origin will not be there.
okay. So it will not the kind of cone is that? With the cone?
It will not be.
Well, yes, then catch.
Origin is included in the type. So if theta is 0, then that can be included.
Right? Mean the cone. See, not the definition, which is you have to be careful. Since we think of this subspace in some sense, subspace contains a zero. Okay. Other definition. So I said a few definitions today. So what's the difference between affine and convex? So convex was lambda x1 plus 1 minus lambda x2 belongs to x. Then we insisted that lambda was now affine is lambda x1 plus 1 minus lambda x2. But we don't insist anymore that lambda is greater than 0. Essentially, any linear combination. So, to give you a simple example, one is convex and another is affine, which is more strict. More strict, yes. So, give you an example which is affine but not convex. So, what we are removing here is lambda simply belongs to. That's the difference between convex.
Affine will be convex, but should not be other than not.
Strict. Convex is strict. So give an example, which is affine but not convex. Valid? No, not possible.
I said every affine sets without convex.
Okay, then how can convex be stricter than affine? Something.
Yeah, convex is not strict.
Okay, so
Convex is
every affine set is convex.
But every convex set are not affine. No, not all convex set are affine.
The first statement.
Every another convex. So take any two point from the affine set.
Okay.
And take a linear combination. That makes one minus one such that summation.
Why was such things?
So it is R enough.
That's all. Specialize it to this. It works for all R, so it better work for subset of 0. That's all. Now we can move to
Affine has a higher restriction. Lambda can be all R. So
essentially it has to be a line. It can't follow a line segment.
Right.
As simple as that. Whatever. So now we'll do something interesting. Hyperplane and hyperspace. Hyperplane everybody is seen, right? So hyperplane by x such that it transpose x. Everybody has seen this in 2 dimensions, one line, 3 dimensions, a plane, and so on and so forth. So what will this A and B called? We call it something. If you're not used to it, that's okay. Not coefficients. It's telling you something, right? There's some geometry going on between A transpose. Yeah, so just think of it to what does it look like? This happened. Yeah. So what is like when what is set? Okay. And what is declare? Yeah, I want something more.
With
Something to do with normal vector and all that. Something is normal to something.
so from the origin, you are drawing a perpendicular to that line. So distance of that perpendicular.
So let's suppose this by hyperplane. A transpose x equal to
So from the origin, you're drawing a perpendicular to that line.
okay.
And the length will be P. So the length is P. Okay, I'm calling it P. The length. So that's correct.
Weird. It's looking that as an action. It's weird. Okay. What is with respect to this? And what has something to do with this?
A1 into A1 is even normal vector.
Let's call it A.
Okay, so A is the normal vector. To the hyperplane.
Okay, what is B? Is B P or what is it? Or some other random quantity? Okay. Why should two be equal to this? I just want to scratch out once.
B is a vector and that's a scalar, right? The length of the
Yeah, once I take the norm, it turns out as a scalar, B is a scalar, so I can divide scalar by scalar. No dimension mismatch.
Yes, so P is the normal vector to the plane. And it has direction.
For the moment has been defined to be the length.
Length of okay, 0 to what is
This length.
so then the shortest path, the shortest segment connecting the origin with the plane will be the perpendicular.
Correct.
So then the perpendicular is the normal.
Yes.
So if it's the and the direction of the normal is A.
Yes.
So then the distance will be B by.
And when we keep calling it normal, Can you give me the why is called a normal?
Tangent and all. How do you say it?
One line essentially. So A transpose something is equal to 0. You get something?
Projection space.
No. Where x and x0 belonging to H. It's true, just by definition.
Yeah.
So what is x minus x0? That's nothing but a vector
Right.
which sits on the plane. Correct? X minus x0 is nothing but a vector. Some x here and some x0 here.
Right.
It's just the vector which is on the hyperplane. And that is A transpose a vector turning out to be 0. Dot product, yes. So this is why it's called the normal. But the A transpose is simply normal to the whole space. And this is as simple as it can be. But you take any vector lying on the hyperplane, then the limit of this, it's normal to that. So that one is fine. Now, why is it that the perpendicular distance is so much? All high school geometry are all done. This we will bring the point. Flash it out. It's not the best, just go.
So what is the question?
Question is what is the perpendicular distance equal to b by log of A? How do you get from this?
So that will be the projection over there,
Okay.
and that way we can get it. You have to calculate it, but we can get the.
In principle, what is it exactly? How would you, like, if somebody tells you this is the right answer, can you convince yourself that in fact is the right answer? Why?
So the x is x-axis, like for this purpose, the x-axis. The projection of that on the hyperplane will be that.
This one.
No, that.
So that's not position on the x-axis, right?
No, so no, I'm saying that. Okay. Right.
Intersection at X projected onto the normal.
That's here, right? But normal is this. So we'll get back this point possible.
So that
But that's not P, it's something else. When we're talking about this distance, right?
this is the projection distance.
Projection of what to what? This point's projection on this line. But isn't it this rather than this?
No, the projection distance is not, it's the distance on the line from origin.
No, so maybe just using different vocabulary.
Okay, we use like,
I agree, is nothing but the projection of on this line. Right?
so we use trigonometry.
Yeah.
This inner angle.
This one or this one?
That one.
Yeah, the bottom near the bottom.
This one.
Yes, and the bottom distance is.
It's complicated.
Yeah.
It's so complicated that it's not easier than that. Why is that correct? Coming up again and again. We'll also place some distance between two hyperplanes and all. So if I give you two different hyperplanes, what's the distance between them?
You are going to do the P minus T distance. Difference of that divided by B.
No, A could be different, right? The two
So P1 is
even minus P2. Okay, how do you convince me that? This might go like this. And I will get a different people. Except they're parallel, that's a different story. But that's not necessarily the way I'm.
If they're not parallel, then they will intersect. There will be zero. It's not for the higher end, but for
Correct.
at least
Yeah, so in one dimension. But it is true, I agree. Otherwise, it is simply the difference.
Right.
Okay. Fine. So this is hyperplane. And what is half space? So let's call it slightly bigger. Then I'll bigger than. So now the most interesting thing we want to solve is the separation between two disjoint convex sets. So suppose I give you two disjoint convex sets. I want to say something about a hyperplane.
There is a separate hyperplane.
I use separation to define.
There is a hyperplane. You can draw a hyperplane that will separate.
Separate
Like it will be different path schedule.
spaces. That's not the correct statement.
So by a hyperplane.
It's a complementary, but not different.
So by a hyperplane, we have two hyperplanes.
Say I was the correct thing from one side. I don't keep saying the same thing.
One convex set will be in the hyperspace and the half space, and the other convex set will be in the complement of the half.
Okay, so what do I want? So let's say this is my one convex set. Let's say I have another convex set, which I don't have any common point. Why do you think that I can always find an hyperspace something like this? It's difficult to refute. It's not that difficult, but will exist something like this. What's the difficulty? Or why would we in fact for convex sets? Think of in two dimensions. Why is it always possible to find a line that separates? By separate, I mean one object is on the left side, other object is on the right side. Is it always possible to do that if these objects are not convex? That's the important thing to notice. Proof is not very difficult. But what is the convexity of these sets? Do you think the sets themselves are not convex? I can still do this. To be clear what I'm trying to do, I have two convex sets with a chart. I want to claim that I can find a straight line which essentially goes in between them. Those words.
So
No. So now what we're trying to understand is the non-triviality of the statement. That if suppose the objects are not convex by themselves, then I still get the same thing. So that's why I need convexity somewhere. And it's very easy to construct example, right? Suppose I had this not a something like this, then say this. Let's say there might be objects. So I'll keep one as convex. As soon as I am allowed to put something non-convex, there's no way you can actually find the line. So all you can find is crooked lines. Possibly something like, I would go very close. That's not a straight line. So what's helping you? Why? Now you can appreciate the convexity is needed first of all. If it's not convex, I can create a counterexample. Now tell me why convexity will help me. The moment you disprove the fact that it is not convex, it's not possible. But convince me that in fact for convex, it's possible to do so. Totally mechanical. So,
So we can take the Then from the two convex sets, we can take the,
I'm not asking for a proof.
just the idea.
Yeah, I'm not even looking for an idea of a proof. So in this picture on the right, I'll say that if they're not convex, we'll not go. All I want is where is the wave coming from in the convex.
If they are convex, then they are, the convex hull is the set itself.
Yes. But that doesn't help me.
Last time, in the last class, you have done something with the distance function.
I'm not asking for this idea. You clear what I'm asking?
Yeah.
So don't try to prove. All I'm asking is what is the idea for a the number of pixel convex. Why would somebody even think about it? If they are convex, something like this is impossible. What property is of the convexity is going to exploit to prove something like that? That's the question. This is very mechanical. Doesn't illuminate anything. What went wrong on the picture on the right, and why does it you can't prove that let's search for which something like this. What stops you from doing that?
I have very weird argument.
Okay, keep it to yourself.
No, I will say.
Where it becomes,
If you play,
when it becomes less weird, then you can. You yourself use weird.
no, I am not thinking weird, but it will play. So, if there will be a play. We can take the projection of those.
Too complicated. I am not looking for a proof.
I think it's because any line passing through a convex object has a single entry and exit point.
Why is that useful? It might be true, but why is that useful? Because we're not looking for intersecting lines, right?
We can keep shifting in real time. We can
No, but whenever we use the 5/12 into 2 points, keep shifting eventually it will blow. So, what's it?
Distance. If you do convex sets, so the distance of two sets will be a unique, having a unique point. And if you move from that point, it will.
That's not true.
grow. It will grow.
It's not true.
And for the convexity part.
It's not true for convex sets. But this have slabs, right? Both are convex at the same distance throughout.
Yeah, I think the distance cannot be lesser
Circles, unique. For two circles, with exactly a pair of points at which the minimum hits.
than. Yes.
So the unique also is possible, equal everywhere is possible. Now, we want to find a
This is one track.
sorry,
No matter how many are there, we just need at least one.
but that's also true here. Right? What went wrong in non-convex case? I think one to say it wrong. Yeah, usually you can, I don't mind to start with visual.
So the uniqueness,
What uniqueness of what?
smallest point.
Not necessary.
No, I'm saying either it will be infinite.
What is going on? What is that?
Because in that picture, in the non-convex picture, if you have that corner point, so the distance, minimum distance achieved from that point, exactly 2 points.
So,
Not neither infinity nor 1.
okay.
But
No, it will be for convex sets also. Take two squares. What's wrong with that?
yeah, there are infinite points.
One,
With unique distance. Otherwise, a unique point.
I just shifted it slightly.
And then it will be unique. So
I
I don't think it can.
will follow the argument. And the argument itself.
So I think irrespective of complexity, like in this example, if we just shift the two spaces, we can still find the line. So the argument is that if there exists a line which passes through both the sets, but has at least two entry points in one of the sets, then for that pair of shapes, then separation doesn't exist.
No, but I will shift the line. Which
It
line?
doesn't exist.
How, that's the problem, right? What is giving you the confidence that with convexity I can do it, but without convexity I cannot do it? I'm just trying to hit that. The convexity is something special to say.
So maybe the only way that the line gets passed between both of them, I don't know if it passes between both of them, is that also it passes between the convex hull. So if, for example, in that case, if you are distant, then there is enough space between for it to complete its convex hull with the line is to pass.
I don't think I follow what you're saying.
So in the sense that
I understood the convex hull what you mean, but that doesn't give you the hope that it will work, right?
So my argument, whatever I'm trying to say, is because you cannot produce two convex sets for which the minimum distance achieved at more than one twice, not infinite, but any finite number of twice more than one.
I don't know what you're saying. I just don't understand what you're saying.
So given two sets, A and B,
Right.
yes.
So
The minimum distance between A and B, either if they are convex, either will achieve at single point, unique
what
point,
do you mean by unique point? There's one point from here and one point from here.
or infinitely pairs of points.
So suppose that was also true.
Yeah, but for the non-convex,
Suppose that was true.
yes.
How do you help you? Line passing.
That guarantees that between two space, the distance are keep increasing or being remain same, and there is a gap to draw a line between.
We're not using the convexity part. I want a convincing argument why convexity helps. I'm not looking for a proof. Which will essentially try to do this.
This will have something to do with that, like that non-convex shape. It kind of fits into that convex.
No, that is just one example I created.
So, I mean, that is never possible in convex. I think
No, that's true, but that's never a full way of thinking. There's something
I mean,
going on with the convexity part, right? The fact that a set is convex tells you something. What is that? It's telling you.
two lines in that shape, 2 points in a convex set. So I have a linear combination of that should be inside that. But that's not possible for a non-convex set.
Correct.
So
I build that from that. That is true, and that's essentially at the heart of the point. So suppose you take a non-convex shape and convexify it. Okay. Is it necessary to overlap if earlier I was not able to find the line? So this example, what is happening that I have to make this complete line. So I'm unable to find straight line. I'm asking, is it possible only if I convexify this set, the two sets will actually have a non-trivial intersection? Okay. Suppose it's possible to convexify that. Then what will happen? And still we don't have a non-trivial intersection.
and then we can pass a line.
So, But I'm just trying to impress upon you what I mean by one. If you keep pushing it away sufficiently, the convex file like this also will not overlap with this. And that essentially will allow you to draw a line. So that means origin itself, I will be able to draw a line. It's only because they're too close to each other. The two non-convex shapes are too close to each other. And that is what is preventing me. And as soon as I try to convexify one, it will eventually overlap with the other. Because if it was not, then I would have been able to make that line go through. Just think about very geometrically. But the fact that the line is not straight is telling you something about the shape. But it will not be convex. Try to work the other way around. So if you take two objects and you are unable to find the line, claim that at least one of them is non-convex. The other way around. If it was convex, you should be able to push it through. Okay, so now, at least for this picture, what really is going on compared to this picture? All we know is that each of them are convex. That's all we know. So any 2 points, linear combination of them or convex combination of them lies completely within that set. That's all we really know. The special property should be somewhat as well. So convex something should be very critical to it.
The line will not lie in either of the convex component.
That's not necessary actually. Let's not get into that territory. Because we're including greater than equal to sign. So I think one of them is fine. We're not excluding. So I don't work with the contribution. That's the easiest thing to work in this particular case. Suppose both are convex and they're not joined. And suppose you can't find them. What will go wrong?
So in line you draw, it will intersect both of them.
Something like that intersected about them.
If they are both of them convex,
Whether they are convex and we need to find the lines. That a line, each line, each line intersects all of them. Both of them, sorry, rather not all of them.
yes, both of them.
Okay. So
So the point is
touching is not excluded. That's the whole point. Touching them is fine.
it might happen that as a line, wherever it is one set is touching, the others for the other set, it is the touching is at some points above and below on that line. So that the convexity, convexity of those 2 points is including the point A also, that is affecting the disjointness.
No, I didn't see any argument to contradict anything. They are being contradicted.
So they are disjoint.
How? So what are you saying? You have 2 objects which are convex, and I can't find a line which is able to separate them. Oh, where is the argument?
So I'm saying that for any line,
There is a line.
yeah,
So it doesn't have a line, so there is one line.
yes. So it will intersect both of them. That line will intersect both of them.
Okay.
So I was taking x equals to 0. This is easy.
Oh, complete the argument. So you're saying X is a line
Yes.
which doesn't separate. What does it mean? Because the line does not separate. It is not a line separate. In real life, it doesn't separate. So what does it mean? It intersects both,
Yes.
at least at one point. Okay.
So I'm saying that for it will at least intersect another one at most at least 2 points.
Yeah. I can easily make that. I can just add a small, and now there is only 1 point possibly for this line. So that's not necessarily true. So not disjoint, but that would contradict, right? Somehow. The contradiction argument, you can't do everything. All you are contradicting is there is no line which separates. Now you have to prove that they are not disjoint. You can't start with disjoint and then everything and then everything and then really contradict. The moral is there. And that's what I want. The people is very mechanical. Please try to come to this distance, that distance, blah, blah, blah. Not very interesting. But that's essentially at the heart of the matter. Things are convex.
Saying visually is very difficult if I just draw what I'm trying to say.
Why is it difficult? Push the circle close to the square or pentagon. What happens? And what is the premise? There exists no L that I'm not defined separates, but hopefully it's clear. Separates means one lies on one side, other lies on the other side. That separates. What does it do? It comes down really. That means you pick any line and do what with it. So there is no line which separates. Pick any one line. What happens?
It will, at least one side, there will be elements from both sides.
Correct. That's all you have to work with. Because if it was, otherwise it will be separated. So there exists such, so for pick any one L. Then, and let's say x1 and x2 are these sets, right? So then x1 is bad. U1 V1 belonging to x1 and U2 belonging to x2. But when I say now in terms of one and one,
What is U1 V1?
some elements of x1.
So there is a line connecting.
No.
Okay, just say what.
U1 comma. It's two elements from each of these sets. You want to say something like right? That's all I'm asking you to write in terms of U1s and
U1 V1 will belong to X2 as U might be myself.
no. So U belongs to, let's say, left
U1
off.
belongs to X1 and V1 will.
So how do I represent this line? So
Sorry.
so then what you want to say is transpose U1 is less than V and transpose V1 is greater than. Right? That's what you wanted to say. One is on this side, other is on this side. Okay, what else? So for picture, just think of intersecting. That's the only way you can actually make it work. So now we are intersecting with no existing line. So think of any line. Let's just think of this line. Would you want to claim that there are points on both sides on this line? What do they tell us in terms of the disjointness is the key? Or you have to show you that there is a non-trivial intersection. That's all you have to really. So you have to produce points which belong to both. So all this part is like this, all this part is like this. Similarly, you can get V2s and V2s. So what? This part and this. Anyway, somehow narrow this down, and there is a non-trivial intersection.
My was for every line, you have 2 points, which is for one.
I was just telling you about.
Another perpendicular line.
Arey yaar, why is my mind sufficient?
I'm
Why
just
do you need
narrowing
paper?
it down by taking.
You'll have another 4 more equations by taking other line.
Not equations, it's just
Hmm?
one visual picture. But
Okay, other line.
not another line. Those 2 points which are touching that point.
Which two? I've drawn everything for you. Just tell me. This is one point, that is another point, this is another point, this is another.
Or whatever is touching for one set, another set, take 2 points,
Okay.
draw the perpendicular lines. For them also in the previous line.
Yeah, that's too complicated. Why not just somehow tell me that if this is true for U1 V1 and this is true for U2 V2. A transpose U2 is, let's say, greater than B, and transpose V2 is less than B. Well got. You want to tell me that there exists something in the intersection of x1 and x2. Right? That's all we really need to consider. Picture-wise, it's obvious. How do I, because this is all I'm given. How do I do this?
The intersection of these planes will lie inside will lie both.
But then what are we use the convexity of it?
Okay.
That's what it is. Somebody need to use the convexity.
So then when A transpose V1 is less than B, A transpose V1 is greater than B. So the line connecting U1 and V1 will lie inside, but the line connecting U1 and V1 must lie inside X1 by definition. Right?
Yes,
So then
that doesn't do anything. That is true. Because that is always possible, right? You just take one convex body, pass a line, it separates into 2 parts. So this is possible. It's also possible. The fact is that both convex, that they have to intersect. That's all we really have to. The picture argument I'll accept for the moment. Picture is clear, right? Forget this perpendicular, I don't want. It's not needed. All you have is this area, this area, this area, this area. Or you have to tell me that there is something sitting in the intersection. That means that is what is going on. Why convexity helps you.
U1 minus V2, A transpose U1 minus V2 is less equal to 0.
A transpose U1,
Minus V2,
okay, is less than equal to,
0.
okay.
And
Similarly to this here.
how you get transpose of U1 minus V2 is how the technical function.
Okay, the limited time let me do this. But I'm seriously asked you to just think through this. This is more or less there. Just line of language. And this will remain with you for much longer, rather than the full command. Who goes through individual instance-based arguments. So let's say these are my two convex sets, x1, x2, and c. C1 this. So distance between x1 and x2. Before this is class. Otherwise, think of meaning. So, let me do the instance such that B belongs to x1, B belongs to x2. Okay. And when it is achieved, that means minimum essentially at point C belongs to x1 and D belongs to x2. Okay. This is the minimum distance. Now, can you do a constructive argument and tell me a particular hyperplane?
Perpendicular bisector of CLT.
Yeah, that is not sufficient, but that's what we bring upon. So, with distance, you can say that, okay, pass it through the point. At what angle is the problem? What angle will make it work? Entity perpendicular. Okay. So what will be the definition of such a hyperplane?
I have a small doubt.
Yes.
What any x1 x2 will achieve?
I achieved.
If you have two open balls.
That's what I'm saying. For the moment, consider the case where it is possible. Not necessary for every possible direct thing. As long as it's close, things are okay. You need the harder thing in your homework. So, okay. So now this I'm given. I essentially want this will also be the maximum separation in some sense. If it's possible for perpendicular, there's the minimum distance looking from the way and which is possible from both x1 and x2. So what should be my affine function essentially a hyperplane?
In C minus D will transpose.
So think of defining A is equal to B minus C and B is equal to square minus C. Well constructed. So if you go back and think of them, it will be eliminating to choose this. Okay. And then think of the function f of x A transpose x minus b. And then we get any point in x1 evaluates to what, and any point in x2 evaluates to what. That's how you have to show that it's less than 0 on one side and greater than 0 on the other. That is writing the out. That's all I've done. So nothing but hyperplane passing through that midpoint is essentially what is A transpose x. I could have differently written. Think of the hyperplane as A transpose x minus A1 equal to B. What we're trying to show is that for any x belongs to x1 and any y belongs to x2, f of x is something 0. That's all we want to clear. Question?
Minus or plus the square.
It's fine. That's what it is. It's also good work. Just one such. It's not unique. Okay, so let's show this. Other one will automatically easily follow directly. So what do you want to show this? So, the size of these functions. This is 600. We have defined. But switched C and D's also. Okay, let's see. Lower than 0. It's one of the two choices. Here. But that's all. I would never consider writing C on the right hand side and D on the left hand side. But that's what the book does. It's me to do that. Okay, so supposing we don't know the direction is going to be, should we proceed? I want to show it's either less than 0 for all or greater than 0. You just fix the sign which works.
If you're writing D minus C, so like the next one. The whole point of that is that the difference between D and I or X is larger than between D and C. So that is substitute that we should probably do.
So we are comparing, right? We are essentially looking at this. That's
We
X.
wanted to prove that.
This one?
Yeah.
Yeah. But that has nothing to do with D theory.
Okay, but like because
That is D is somewhere D plus C this norm of L plus and minus.
We will make sure that it works out. So start with only one of them and try to show that it's not true. So let's suppose we want to show this. If you get a difficulty, then switch the sign. Because I don't know right now what have been done and what I have done. But construction wise is okay. Because switching the signs should not create trouble. Okay, so what will be the strategy? If I want to show that for all, see, it's simply one sign. That's what I want. But for all x belongs to x1, f of x should evaluate to either greater than 0 or less than 0. What should I do for that? And remember, we use convex example. If the interest of making sure that it works, let's just do this. Okay, so now this is in fact correct. And I can write f of x in terms of C's and D's as minus transpose x minus 1/2 D plus C. So you can check. That's another way of writing it. So let's try contradiction. What do I mean? But look at any point sitting in x1 for which this is less than 0. So U belongs to x1. Okay. Why I don't like such products? That's so mechanical fields. So now write f of u C transpose. Just nothing they didn't C is also equal to D minus C transpose U minus D plus R D minus C whole square. This is the compute. I think there is interesting going on. So no convexity is being used. So we know that this is true by assumption that so given f of u is less than 0, do we get this? That's the previous equation. From here, if f of u is less than 0, we can see C will multiply with some to produce something positive. So, because the overall thing is negative, this part can be negative. That's what will turn out. And this, it's just an expanded form of the same f of u. So, take the derivative of d by dt. It's a derivative. So, let me plot. By so t. This is the value as equal to 0. That is just the computation. There's nothing going. Identity. Let's call it. For t between 1 and 0, we get this b plus t times u minus d minus c. Within the geometry of what we think, so remember, the closest point here, C is the closest point here, and B is some point inside. Okay. What are you trying to say? Connect U minus D, scale it up by 2, and look at appropriate distance with respect to C. That distance, for small enough t, is smaller than the distance between D minus C. That's what all of this is implying, but which goes against our intuition.
Yeah.
No, not for the triangle, not for the moment. But essentially, convexity will have this. Convexity is not convex, it's possible. Right? Because if I suppose I create a non-convex part of this, then I can construct a way for which this d plus t minus c is actually closer to c than this distance. And where the convexity will come and help us. So because of convexity, this is not possible, so that is not possible. Is steps clear? Like, again, never look at the mechanical part of the proof. These are all just bottom line is this, that if that inequality is not correct, then you're creating a rule such that this t times d minus d plus d is closer to c compared to d minus c. And this point is nothing but because of complexity of this. This also belongs to X1. So creating a new point B trigger, which is closer to C than D. But by the definition, B and C are the closest to point. So we are not possible. So by convexity, so this is where convexity comes in help. B plus P U minus P. So another way of writing lambda x plus 1 minus lambda. This one brings it to be small, less than equal to 1. Also belongs to chi1 implying a contradiction B. It is closest. So the field direction exactly follows as it is. You just flip the roles of x2 with respect to x. All right, we'll move over time. Let's stop.